I'm Anil Kumar, and in this particular video, we are going to discuss the most important application of calculus, and that is to capture rate of change. As you know, in this world, things are all related. A small change in one makes a major change in another, right? So, with the help of calculus, we are going to describe and predict the phenomena of change. So let me write it here. We are going to describe and predict phenomena of change, and that is where the rate of change comes in. Now, there are huge applications of this. For example, you must have noticed that, if you are filling a tank with water, for example, right? So if you fill the tank in water, then what you notice is that the level of the water changes depending on the container. The rate of change of the height of water can be predicted, correct? So that's a lot of dynamics. You could also see examples where there is oil spill, for example. Now that is volume. And what really happens here is that the oil spreads over the surface. Correct. So we could predict with the rate of oil spill, at what rate is the oil spreading on the surface of water. Likewise, there are so many applications. We are going to consider these applications one by one. So the topics which I'll discuss we'll first try to understand some basic concepts along with formulas which you should remember. As you can see here, we could have different kind of containers. So you need to know the formulas for surface area and volume of those containers, right? One of the major applications is, of course, relation between displacement, velocity, and acceleration. We'll take a few examples. In fact, I'll take up just a sketch because we have already discussed this topic at length earlier. Now, implicit differentiation is something which you need to refresh with. Since you can see here, we are trying to relate volume with area and working with time. So there are things related, and we may do differentiation with help of with respect to time for all different quantities. So you will need the concepts of implicit differentiation. So I'll take up an example here just to refresh it. And then on rate of change, we'll take a few examples just to provide you with like slope of tangent, right? And then we'll also talk about related rates of change. And we'll consider many examples on maximum and minimum and also optimization. So let's see. So there is a lot to cover in this, and I hope you find it interesting and useful. So let me begin by giving you a few formulas which can always help you to solve questions which we are going to work with. I hope you remember what a square is to begin with. That's the simplest thing. Area for the square is, if S is the side, it is sides S square, right? And the perimeter is 4 times S, right? Now if I convert this square to a three-dimensional figure, for example, a cube, correct? Then what happens? So in case of a cube, you know that we are not talking about surface area. So as soon as you go to three-dimensional figures, you start talking about not just area but the surface area, since now there are lots of surfaces, 6 surfaces, front, back, top, bottom on the sides, each having area of S square, so it becomes 6S square. Perfect. And we talk about volume, correct? So volume is S cube. Then we'll consider different shapes. We'll take up cylinders, right? So if we have a cylinder like this, we are talking about surface area and volume. in that case the formula for surface area will be, there are two surfaces which are circular, that gives you 2 pi r square, right? And then the lateral surface 2 pi r h. So we'll add this to 2 pi r h. As far as the volume is concerned, area of the base, which is pi r square, times the height h. So we need to know two things to describe a cylinder. One is the radius, the other one is the height. Now we have some examples related to cone also in this particular exercise, which is again a three-dimensional figure. For cone, I'll just give you volume formula which we are going to use, and the volume is 1/3 of that of the cylinder. So it is 1/3 pi r square h, right? So these are good formulas to remember, especially to do examples which I am going to come up with. Then we'll also be using at many times distance formula, right? So distance, remember, is given as square root of x minus x1 whole square plus y minus y1 whole square. So that's the distance formula. If you have to minimize the distance, in that case, even distance square could be minimized, correct? So these are few things to remember. Implicit differentiation formula is also very important to remember, and that is that if I want to find what is dy by dx, I could actually find as with respect to two different quantities, I could say what is du by dt, for example, and then I can find what is dt over dx. Now normally we don't write like this, but anyway, you could do something like this also to find the derivatives with respect to the related quantities, right? So now let's begin and take examples one by one. So the first one here is to really understand what rate of change is. So what I've done here is taken a sketch. So we have a sketch, so we have a sketch of velocity here. So let's read the question. It says, sketch the displacement and acceleration graph from the given velocity graph, right? So we are given velocity graph, so we know v of t. That is what we are given. Now we need to sketch the other two. One is the acceleration, right? So the acceleration, you know, is derivative of velocity. So that we can find by drawing tangents on this graph, correct? So that should not be very difficult. You could always pause the video and work it out. The other part here is that you have to think how to sketch displacement graph. How to sketch displacement graph, where you know that velocity actually is derivative of displacement. So you have to do the reverse calculation kind of thing. So you have to think, you have to go back and think. So that becomes really interesting. We call it antiderivatives. We'll be learning this later, but how, of course, here we'll understand as technique of graphically doing it. So that makes it very interesting. Okay, so let us first see how to sketch the acceleration. So first we'll go in this direction. That's simpler. So what we are given here is the velocity function and turning points. If I draw a tangent here, these turning points, the slope of the tangent line is going to be 0. So they will correspond to a 0 on acceleration graph. So we have two zeros, right? So we have two zeros here. Now the other thing which you notice here is that this part of the curve, the slope is positive, right? Slope is positive. That means whatever value of acceleration is, it is above this line, it is positive. Immediately after the turning point, the slope is negative, correct? So that gives you an idea that the graph of this should be kind of like this. So we'll just make a parabola here, right? So these are not accurate, we are not taking any values. Okay, there are numbers written here which could be used, but at present I am only interested in understanding how to sketch these graphs rather than how to calculate their values and get to their equations. Imagine these numbers are not there and then we are working, okay? So that gives you the acceleration, very simple. You understand, derivatives will represent slope at every point, right? So this is slope of velocity. That is what acceleration is, correct? So you'll also see if you're working with polynomials, derivatives, the order of derivative is one lower, correct? Now, getting back to displacement, we know now that we are looking for a graph where tangents will be represented by velocity. So we have to work the reverse way. Okay, so how do we do that? So on velocity graph, we have 3 zeros. Do you see these 3 zeros? Now these 3 zeros are the turning points on the displacement graph, correct? These 3 zeros are the turning points on the displacement graph. Now what you observe here is this part is negative, correct? On the velocity graph, this part is negative and this part is positive, right? So that means the slope on displacement should be negative along this side, perfect, with a turning point here. So that makes some sense. So all along from minus infinity to 2, we are looking for a negative slope. That means the curve is coming downwards. Do you see that? So what you could think about is something like this, coming downwards. Do you see this? And turning at this point. You get an idea. Now here to here it is positive, correct? Here to here it is positive, and then it again happens to turn. So somewhere here we should have a turning point. So I have to go like kind of positive, and then somewhere here I have to turn. Do you see that? So that's the turning point. So that is how you could make your displacement graph. So I hope you're getting the logic. And then again, it is negative all throughout. So this curve of displacement has to come down until to when it turns. So we'll just move downwards and then turn here and then go up, correct? Giving you a graph of displacement. So I hope that makes it simpler to understand how to sketch this graph. Perfect. So it's kind of a review for you before we move on to rate of change. Think like this. So we are still not on rate of change, but we are working on rate of change, but it's kind of a review for you. Okay. Another question here is, we'll see how to find slope of tangent to an ellipse, which is x squared plus 4y squared equals to 25 at the point minus 3, 2. So we'll learn implicit differentiation here. We are given x squared plus 4y squared equals to 25. An ellipse could be sketched something like this. Okay, so we'll just go like this. Okay, anyway, so that becomes an ellipse, and we are looking for minus 3, 2 tangent line. So minus 3 is somewhere here, so let's just draw a tangent line here, correct? So that becomes the tangent line at the point which is minus 3, 2. Okay. We need to find slope of this tangent line, so we'll differentiate with respect to x. Now x is our independent variable, so we'll differentiate everything with respect to x. So we could write this as d dx of x squared plus d dx of 4y squared equals to d dx of 25, correct? Now d dx of x squared is 2x, and here when we do d dx of 4y squared, we get 2 times 4 as 8y, and we get dy dx. Do you get an idea? So that is the implicit differentiation we are talking about. So I've basically taken up this example only to review implicit differentiation. So we can now isolate dy dx, bringing 2x on the other side. We get 8y dy dx equals to minus 2x, and we do get our answer, which is dy dx is equal to minus 2x over 8y, which is minus x over 4y. Correct? So that becomes a general formula. Correct? That is a general formula. Now we need to find slope of tangent line at a given point. So we'll substitute these points. So we saw dy dx at a given point, which is minus 3, 2, is equal to, we'll substitute this value, minus 3 for x, and let me write 4 first, 2 for y, and that gives you minus minus is plus, right? So plus 3 over 8. So as you can see, the tangent line has a positive slope, and it makes sense. So that's a kind of review on the implicit differentiation. Most of the time we'll be differentiating with respect to quantities of different types, right? So remember, see this part. Derivative of 4y squared was 8y dy dx, right? That's kind of important to understand. And now let's move on and take up an application question. Here is our first example on related rate of change. The question here is, a pebble is thrown into water and causes circular ripples to spread outwards at a rate of 2 meters per second. Find the rate of change in area of the circle. There are two parts to it. 3 seconds after pebble falls into the water, and second part is when the area of the ripple is 9 pi meters squared. So the idea is that as soon as the pebble is dropped on the water, you will see the waves being formed, right? So these are the waves which are in the form of ripple, and they move in all the directions, right? So they just move in all the directions. As the radius increases, the area increases, right? So what we are seeing here is a relation between two things, which is let's say radius r and the area. So we need to relate radius with area. So that's the first thing. So whenever you look into a question, you should know what parameters to link. So we get our equation as area equals to pi r squared. So that's an easy equation. For a circle, the area is pi r squared. Now, how do I find the radius? So that is where the second relation comes, and that is we are given the rate at which the ripples are spreading outwards, and that is 2 meters per second. Now this rate is with respect to time. So what we are given here is in a way, rate is 2 meters per second. That means the radius is increasing with 2 meters per second. So along one dimension, this is along one dimension. So we can say dr dt is 2 meters per second. Do you get an idea? So that is the second relation. So radius is increasing at the rate of 2 meters per second. Correct? So both the quantities, area is also increasing with time, radius is also increasing with time. So we know area is also a function of time. Correct? Since area is a function of time, now area is a function of time, you can see, because if the radius increases, area increases. This is very important to understand. So at this stage, we can do derivative with respect to times. Do you understand? So this part, which I have written here, is to understand the question and the approach. Now, we can find what is the derivative of area with respect to time. So what we get here is dA dt is equal to, this is now implicit differentiation. We are not differentiating with respect to radius. We are differentiating with respect to time, right? So what we get here is 2 pi r dr dt. So that becomes the equation to work with. And now we can do each part, which is A and B, right? So we have now two parts to work with. So that is how you have to understand how to solve such questions. Moving forward, it will be much simpler if you adopt this kind of an approach, right? Okay, so now let's look into it. It says find the rate of change in area of the circle, which is this, 3 seconds after pebble falls into water. So after 3 seconds, so we know time now is 3 seconds. Now in the formula there is no time, correct? There is only radius. So how do you get time into picture? So after 3 seconds, what happens? So what we can do here is we need to find what radius is going to be with time, correct? So we know radius is increasing at 2 meters per second. So it will be twice time per second. Do you see that? So twice t. So after 3 seconds, we can find what radius is. So radius is going to be 2 times 3, which is 6 meters. You get an idea. Once you know this, and we already know what is dr dt is 2 meters per second, we can now find the change in area. So I hope you appreciate how we have to do such questions, right? So we are talking about time as 3 seconds, and at that time radius is going to be 6. And now we can substitute these values to get the answer. So we get 2 pi, r is 6 for us, and dr dt is 2. Right? So calculating this, so I'll write the exact values at present. So it is 4 times 6, 24. So we'll say this is 24 pi. Area, units are meter square per second. You see that? That is how you're going to solve the questions. Now in part B, the question is when the rate of ripple is when the area of the ripple is 9 pi meter square. So now we have to find rate of change in area of a circle when the area of the ripple is 9 pi meter square. So in this particular case, we are now given area. So we say if area equals to 9 pi, what is the radius? So the formula is pi r square. That should be equals to pi r square. And from here, pi and pi cancel. We get 9 equals to r square, and that gives you r as 3. Okay? Now you know what r is, and now you can say that rate of change of area with respect to time when r equals to 3 will be equal to, substitute in this formula, which is rate of change, 2 pi times 3, and dr dt is 2. So what we get again here is 2 times 2, 4, 4 times 3 as 12. We get 12 pi meter square per second. Is that okay? So likewise, you could do such questions. I hope that is clear to you. You could get the units directly by placing them along with your calculations. For example, r was in meters, right? And dr dt is in meters per second. So this is meters per second. So when you calculate here, you could write 3 meters. So you could write meters here for 3, and for rate of change, meters per second. So you get meters square per second. Do you see that? So likewise, you work with units also. It's a good idea to place units along with the numbers in such cases. I hope that's clear, right? So now let's take up the next example, which is on cube. The question here is, the edge of the cube is expanding at the rate of 4 centimeters per second. How fast is the volume changing when each edge is 5 centimeters? At what rate is the surface area changing when the edge is 7 centimeters, right? So now we are talking about a cube. Now in case of a cube, what is the formula for volume? So for cube, volume is side cube. Is it okay? And what is the formula for surface area? Surface area for a cube is 6 side square, correct? So that is when we are given a cube. Let me just make one here. So we'll just make Okay, so that's an easy way of making a cube, where we are given that each side is S units. Is it okay? So that is how the cube is. So volume is S cube and surface area 6x squared. Now the question is, the edge of the cube is expanding at the rate of 4 centimeters per second. So we are given that the change in dimension is 4 centimeters per second. You get an idea. That is what we are given. How fast the volume changing when the edge is 6? That means we have to find this change with time, dv dt, right, which will be 3s square. How fast it is changing when it is 5 centimeters. So we can just plug in 5 here, right, times ds dt, I'm sorry, times ds dt. So we can plug in 5 here and get the answer. So we get change in volume will be 3 times S is given to us as 5 centimeters. It's good to write dv dt, where S equals to 5. So I'll write here 5 centimeter this time. Is that okay? Square times ds dt is 4 centimeters per second, so that you take care of the units also. Now we can do 5 times 4, 20, and 3, 60, but 5 square, right? So it is 25 times 4, which is 100, and 300 we get. So we get 300 centimeter cube. Do you see that? Centimeter cube per second. 5 square is 25 times 400, 3. Okay, so that is how you can take care of units as you move along. Now the second question here is based on surface area. Formula for surface area is 6 s square. Each surface is s square. There are 6 surfaces, and we want to see what rate is surface area changing when the edge is 7 centimeters. So let's find rate of change of surface area. So rate of change of surface area with respect to time is 12s ds dt, correct? And we want this surface area change with respect to time when s is 7 centimeters. So we'll substitute that value now here. So we get 12, s is 7 centimeters, ds dt is given to us as 4 centimeters per second, correct? So we can now multiply these quantities and get our answer. So let me use calculator. So 12 times 7 times 4 is equal to 336 unit centimeter square per second, right? So that is how you should be doing it, right? So let's move on now. The question here is, a conical tank is of radius 3 meters and height 6 meters. Water is added to it at a rate of pi meter cube per minute. Find the rate of change of water level when height is 2 meters. So first step is to sketch. So let's say we make a cone here. We are actually given here the ratio of radius to the height. So let me just draw a vertical line here. So what we are given here is that the height is 6 and the radius is 3. Now if we say that the water level is rising, let's say water level is rising, and we need to really find rate of change of water level when height is 2. So let's call this as the height h for us. Now when we are working with conical tank, we should know the formula for cones, right? So volume is 1 by 3 pi r square h. Now in this formula we have r as well as h. We need to relate these two variables somehow. In cones, we'll use always similar triangles to relate. So if you look at it, the big triangle here and this small triangle. So at any instance of time, let R be the radius and H be the height. It forms a cone, right? So at any instance, we can say that the ratio, the big triangle and the small triangle is similar, so the ratio of their corresponding sides will always be same, right? So we can write from here that height, let's write down these relations here. Height over radius is equal to 6 over 3. 6 over 3, which is 2. And therefore, we can write that the radius is half of the height. So radius is half of the height. Now if I substitute this value here, we get volume as equals to 1 by 3 pi height over 2 whole square times h. So if I open the bracket, I get 1 by 3 pi h square by 4 times h, or pi by 12 h cube. So now we have volume in terms of height. So volume becomes function of height. From this equation, we can easily find rate of change of height if we differentiate both sides with time t. Correct? So what we get here is dv dt as equal to pi over 12 times 3 h square dh dt. So we have an expression to calculate the rate of change of height. Now if you see, we need to find rate of change of water level when the height is 2 meters. So we need to work out what is, so at 2 meters, height is 2 meters. Well, in this formula, only height is required. So we can just substitute that and figure it out. And we already know that water is being added at a rate of pi meter cube per minute. So we know dv dt is pi meter cube per minute. I have purposely taken such values so that we can easily calculate the answers without using calculators. Now, we have dv dt equals to all this. We can isolate dh dt and figure out what this value is at height equals to 2. So first let me write dh dt as equal to, this can be simplified a bit. Let me do that first. 4, right? So we could write this as 4 over pi h square, correct? dv dt. Now dh dt at height equals to 2, we'll just substitute 2 here. We get 4 over pi 2 square times dv dt is pi. Now in this expression, as you can see, 2 square is 4, pi and pi cancels, and we get the rate of change is 1 and the units are meters per minute, right? So the answer is rate of change of height is equal to 1 meter per minute when the height is 2 meters, right? So I hope all the steps are absolutely clear. So we can always find rate of change by relating the two variables. Let's move on to the next example. Now you know the concepts. I'd like you to answer these multiple choice questions. I have a few of them for you. The first one here is, an object is moving in the clockwise direction around unit circle. As it passes through point half square root 3 over 2, its y coordinate is decreasing at the rate of 3 units per second. At what rate is the x coordinate changing at this point? So that's the question for you. I'd like you to pause the video, answer the question, and then look into my suggestions. So what we are given here is kind of like this. This is, let us say, a unit circle. So let me just make the coordinates. Where a point is moving in a direction, clockwise direction. So in this direction, right? So in this direction. So at a point half times square root 3, that seems to be a 60 degrees angle, right? So at times they might just give you 60 degrees. Unit circle 60 degrees. without giving you the coordinates, correct? Without giving you the coordinates. So that becomes the point which is half and square root 3 over 2. Now at this point we are given that the y coordinate is decreasing at the rate of 3 units per second. So we know dy dt is minus 3 units per second. So it's right, units per second. So decreasing means negative. That is very important to understand. Is it okay? Now as far as the equation is concerned, which relates x and y, we can write x square plus y square is equal to 1 square or 1. So that is the equation of a circle which relates the movement of particle along this path, right? Now differentiating with respect to time, both sides, what do we get? We get 2x dx dt plus 2y dy dt equals to 0. So implicit derivation is very important. Okay, so now that's what you get, and we need to find dx dt at the given position, right? We know the value of x and y. X is equals to half, y is equals to square root 3 over 2, and dy dt is minus 3, correct? So we can isolate dx dt from here. We get dx dt as equal to, we'll substitute the values later. We can take this on this side, so it is minus 2y dy dt divided by 2x. Is it okay? So that is the value of dx dt, which you could simplify cancelling 2's, and then we get minus y over x times dy dt. So that becomes a general expression which could be used for any point. Now since we are interested in a particular position, we can say dx dt, the rate of change of x, when the point is half, let's write x equals to half, is what? Minus of y value is square root 3 over 2. Let me write here square root 3 over 2 divided by x, which is half, so I'm like 1 over 2, right? 1 over 2. dy dt is given to us minus 3. Minus 3. So that becomes the value, right? You can always cancel 2 and 2. Minus and minus becomes positive, and what you get here is 3 square root 3 units per second. So 3 square root 3, which is option B, is the right option, correct? So it is not all that difficult once you understand the concept, right? Let's take the next example now. Here is another multiple choice question for you. A water trough with vertical cross section in the shape of an equilateral triangle is being filled at a rate of 4 cubic feet per minute. Given that the trough is 12 feet long, how fast is the level of water rising at the instant that the water reached the depth of 1.5 feet? 4 choices are given to you. You can always pause the video, answer the question, and then look into my suggestions. So let us sketch a triangle first, representing the cross section, and then we'll figure out the volume, right? So, okay. So this is an equilateral triangle. So when I say equilateral triangle, it means that the angles are 60 degrees. So let's say all the angles are 60 degrees, all these sides are 60 degrees. Now, if the water level is rising, let us say, let me just divide it into 2, and then let us say that let's say we are somewhere here. So in this position, let us assume that the x is the height of the water, right? So I'm assuming x to be the height of the water at any time. Let's talk about the special triangles, right? So in a special triangle, if this side is 60 degrees, then the sides of the triangle are 1 to square root 3. So that's the ratio in which the sides are. And what is going to be the radius of this? I mean, half of this base will be. It is going to be x divided by square root 3, right? That's this side. So this becomes x over square root 3. You get my point. So in a triangle, or you can use tan of 60 degrees to work it out. Correct? Either way. So the idea is to relate these two parameters. Once you do that, then it's kind of simpler. Is it okay? Now we can always write the equation for area of cross section and then the volume, right? So now, what is the area of this triangle? The whole triangle, the water area will be half base into height, right? So it is half of base will be, this is x over square root 3 this side, x over square root 3 the other side also. So it is 2x over square root 3, right? Half base into height, which is x. So that becomes the area. Now, what is the volume? Volume will be area into the length, which is 12. So you could always simplify this, yes. 2 and 2 cancel, we get x squared. And volume will be 12 times this. So it is 12 times x squared over square root 3. So that becomes the volume for this particular triangular trough. Now we are interested in rate of change of height, so we can differentiate both sides by t. So we get so both sides by t. dv by dt is equal to 12 over square root 3 times 2x times dx dt. Perfect. Now, when we say that the equilateral triangle is being filled at a rate of 4 cubic feet per minute, that means we are given rate of change of volume. Being filled means positive, 4 cubic feet per minute. Right? How fast is the level of water rising at the instant that the water has reached a depth of 1.5? That means x is 1.5. That is what we need to figure out, right? At x equals to 1.5, what is the rate at which height is rising? It means dx dt. This is what we need to find. So we can actually plug in the values, or better still, let's isolate dx dt so that we get a general formula. So we get dx dt is equal to, that becomes square root 3, taking it on this side, right, divided by 24x times dv dt. Now to find this value, what we can do, we'll just substitute our values and find the answer, right? So now we know that dx dt should be equal to, let's substitute the values, square root 3 over 24 times x, which is 1.5, and dv dt, which is 4. Okay, that's what we get. Now this is equal to, we can just multiply this. So 4 goes 6 times, 4 times 4 times 6 is 24, and then 6 times 1.5 is 9, right? So we get here square root 3 over 9. So square root 3 over 9 is our answer, which is option B. Correct? So that is how you can actually solve this question. Now it's kind of important here to either apply the trigonometric formula, which you know what is tan 60 equals to. Let me write down. You could do tan 60 degrees is equals to square root of 3 to find the relation between the two, right? Since this angle here is 60 degrees for you. Is it okay? So since this angle is 60 degrees, we know this ratio has to be square root 3. And from there, knowing one, we get the other value. Perfect. Then it is kind of simpler to work with. I hope the concept is clear. So let's move on and take up the next question. Now here is a thinking question on related rate of change. The question here is, a railroad bridge is 20 meters above and right angles to a river. A person in a train traveling at 60 kilometers per hour passes over the center of the bridge at the same instant that a person in a motorboat traveling at 20 kilometers per hour passes under the center of the bridge. How fast are the two people separating after 10 seconds? So that's the question for you. You can pause the video, think about it, and then answer. So this is actually a 3D kind of a situation. So let me draw XYZ planes, right? So let's say we are drawing like this. So that is my XYZ plane, where that portion is the portion where the train is going, let us say, right? So let us say that the train is moving over the bridge, kind of like this. Railroad bridge is 20 meters above and right angles to the river. So, and let's say this river is flowing down below here. So that is, let me draw another ring. Let's say this is where the river is flowing. Okay, so that is, difference is 20 meters between these two. So I hope the situation is clear. So what we are saying here is that the train is moving like this over the bridge and the motorboat is moving like this, let's say like that. Do you understand? So that becomes the situation. Now we need to find the angle of separation between the two. That means at any instance of time, we need to find, the distance between the two, which is this side. So it's like a 3D figure, right? This is what we need to find. So I hope the situation is clear to you. So if you think about this to be a box, so let's say we just complete this box now. You can find this distance as, let's say we call this distance as S, let's say separation between the two, right? So from this figure, you can find this as a square root of square of all the three quantities, correct? Now what are these three quantities? We know the speed. A person in a train is traveling at 60 kilometers per hour. So in time t, it will move a distance of 60 t. Right? And under the bridge, motorboat is going at a speed of 20 kilometers per hour. So this will be 20 t. All these units are in kilometers. Therefore, this height, which is given in 20 meters, I'll divide this by 1000. So this height will be 20 by 1000, which is 0.02, let us say. Is it okay? That becomes the height, 0.02. Okay. So now, separation S, let me write this as a square, or we will write square root of 60 square, 60t square plus 20t square plus 0.02 square root. Using distance formula in 3 dimensions, right? So think about, or you could do it like this also. You could actually first find x square plus y square, which is this much, right? And then x square plus y square, and then this height square. So either way, you can work it out. So that becomes your formula for separation. Now for easier calculation, since we are writing down to a whole number, this number 0.02 square is as good as
0. It approaches 0. So basically it becomes a 2D problem. Do you understand? It becomes a 2D problem, right? So that is the value at any instance of time. Now I wrote this formula basically to find the initial values, right? We are saying how fast are the two people separating after 10 seconds. So let us find initial conditions. So at t equals to 10 seconds, what is the situation? Is it okay? So at t equals to 10 seconds, what is the situation? What is x, y, and z? So what we are doing here is we are taking x along the boat axis, y along the train axis, and that is z. Correct? So in general, we can write here that s square is equal to x square plus y square plus z square. Okay? So that becomes our general equation. Perfect. In which we have realized that z square is a very small number and it can be neglected. Correct? So we could write this as approximately s square is equal to x square plus y square. Now differentiating with respect to time, what do we get? We get 2s ds dt equals to 2x dx dt plus 2y dy dt. Perfect. We need to find ds dt. We know all these parameters, right? So all these parameters are what? Let's write down on the side. dx dt is 60. The speed at which the train is going, dx dt is the boat speed, which is 20. dy dt is the train speed, which is 60. And we have to find the separation s, and we also have to find x, y, and s at t equals to 10, right? So if I write t as 10 here, then what do I get? I mean, I have to convert the units from kilometers per hour. Let's convert 10 seconds to hours. That is better, right? So it becomes 10 divided by 60. It gives us minute, and then again 60. So that much. So which is time as equal to, let me write down here, time is equals to 1 over 360 hours. Is that okay? 1 over 360 hours is 10 seconds. So the value of x is going to be 60 times t, which is 60 times 1 over 360. Is okay? 60 times 1 over 360. The value of y, 60 is y for me. Okay, let me write y here. The value of x is going to be 20 times 1 over 360. Right? So these values are 1 over 6, and this is 1 over 18. So we know x, y. Let us also find separation s, which we can find from these values also, right? A square plus b square square root. We can do this. So s will be equal to square root of 1 over 6 square plus 1 over 18 square. Since 0.002 square is very small, is it okay? So let's use calculator, find this answer. So we are calculating square root of 1 divided by 6 square plus 1 divided by 18 square, which is equal to square root 10 over 18. Is it okay? So we have found all these values. We can calculate rate of change of separation using the derivative, and which is ds dt is equal to, we can divide all this by s, right? 1 over s times x dx dt plus y dy dt. Correct? So it is a three-dimensional situation, but since the height is very small, we can treat this as two-dimensional and get the answer, especially in the multiple choice question. That's the whole idea, right? So 1 over s means I could write this as 18 over square root 10. And here x is 1 over 18 times dx dt is 20 plus y is 1 over 6 times dy dt is 60. Right? So that gives you the answer, correct? Now let's calculate. So within bracket, actually we could open and do it easily. Since I have lesser space, I'm calculating, right? So we have 20 divided by 18 equals to, plus we will do plus 10 I could have written, right? Plus 10, 60 divided by 6, right? So we get 100 over 9, and we'll multiply this by 18 and we'll divide this by square root of 10. We get 20 square root 10, which in decimals is equals to 63.24, right? So we get our answer as 63.24. Is it okay? So option C is the right option. Perfect. So I've done a lot of work here in a small space. It actually requires a lot of space. I was thinking where to fit in what. But let's go through it once again. The situation was that we have a bridge over which a train is going at 60 kilometers per hour, and therefore this distance along y will be 60t. A boat running perpendicular, but along the x-axis, is going at a speed of 20 kilometers per hour, and therefore the distance will be 20t. Separation between these two is going to be square root of sum of these three squares. Now since the height is very small, we have neglected that. That's the whole idea, right? And then we have solved it like a 2D problem. We have neglected this part, right? Since that is not making a major difference. Now differentiating both sides, we get our equation, and to get the exact value, we work on the initial situation. At t equals to 10 seconds, which is 1/360 of an hour, if you multiply this by time, all these speeds, you get distance, x and y, and also the separation. Plug in the values and calculate the answer. So with this, I think you get fairly good idea about rate of change applications. Now there are many other examples which I have, especially where we'll be finding optimization, maximum, minimum. Those I'll attach as annexure to this. So I'll provide you with these links which you should go through. But I hope you have got the idea. Feel free to write your comment, share your views, and if you like and subscribe, it'll be great. Thank you and all the best.